Good afternoon, and thanks for joining us today for SME's Manufacturing Technology Series webinar. In today's webinar, using additive metal for tooling repair applications, we will learn about how AM is being touted for its use in prototyping and high-value applications. But there is much more to its capabilities, and you're going to find that out today. You'll learn how direct energy deposition, or DED, can be utilized to build, enhance, and repair components, including tools. Good afternoon, I'm Carl Mitroff. I'm the MT Series Content Manager, and thank you for joining us. Before we get going, I just want to cover a few housekeeping items for today's webinar. Now, you'll recognize right away that your microphones have been muted. And if you have any questions regarding the functionality, please use the chat feature. So if you're having technical problems, post a question in the chat feature, and we'll try to respond that way. If you have technical questions you would like to ask our guests today, our guest speakers and presenters, please use the Q&A box. We'll be monitoring both throughout today's webinar. And in the event of any technical glitches, just know that we are recording this webinar and we will make it available within about 24 hours on our MT Series website. So moderating today's presentation is Melanie Lang. Melanie is FormAlloy's co-founder and CEO, and she is motivated by developing disruptive technologies, including geometrically complex components made from exotic materials. Melanie has over 15 years experience as an engineer at Lockheed Martin and Boeing, and she currently serves as Vice President of Legislative Affairs for Navy League San Diego, and is a Women in 3D Printing Ambassador, and again is very active with America Makes Executive Committee. Thank you, Melanie, for helping present today's webinar, and I'll kick it off to you.
Thanks so much, Carl. I'm really excited to be here. There's a picture of me on a recent visit to Huntsville, where I was standing in front of their hot fire test stand, and that's where they do a lot of their hot fire testing of additive components and other things that they're trying to test before they actually go into production. So just wanted to kick it off with a little bit of fun. And I also want to introduce Laura Eli. Laura is the Director of Programs at the Barnes Global Advisors, where she leads a team of industry-recognized additive manufacturing experts in providing specialty, technical, and strategic solutions to solve customer problems. Prior to joining the Barnes Global Advisors, she was head of technology for GKN Aerostructures, and I think that's a good lead-in to this picture here, Laura.
Absolutely. Yeah, this is a picture of the equipment that really launched me into additive manufacturing. So this is a directed energy deposition piece of equipment. You see the really large orange KUKA robot, and then the business end of is the wire feeder, and I think it was up to 20 kilowatt laser power. Tend to operate more like at 12, which is not quite so much, but you know, you could blow some pretty big holes in things using that type of laser power. And so that was it's a representative of where I started my journey, and then it's also what launched me into the opportunity to join TVGA and serve in the role that I do now.
Awesome. Well, we're so excited to be here with you all today to talk a little bit more about DED, what it is, applications, and specifically on tooling applications, because you don't hear as much about that. It doesn't always make the news highlights, because it's not necessarily as exciting in some people's views, but certainly has big impacts to business and definitely a great use case for additive. So before we dig into that, I just want to introduce a little bit about who I am and what we do at FormAlloy. We are a directed energy deposition manufacturing solution company, so we provide machines and manufacturing solutions to build out customer applications. So we have our machines that have our in-process monitoring and control that make them smart, so you can do things like tooling repair and builds. We have software that can help you make good decisions about the process parameters that you're using and be able to record the build information. And then we offer the engineering and production services in-house to help customers with their end-use applications as well. You can go to the next slide. And really what we're here to talk about today is what is DED, how does it work, and all the exciting things you can use it for. You can see on the video on the left there, that's a video of DED in action. So how the process works is that you blow powder, and we're using a coaxial nozzle in this case, and you blow powder into a laser spot size, and then components can build up layer by layer. There's a 5-axis capability, so you can get some more of the complex geometries. And then, of course, with this process, since you are blowing the powder where you need it, you can put material onto an existing part. That kind of leads us into the different use cases for DED. The first being form, so that's building new components. You can do complex geometries with that, or simple geometries. You can enhance components, and by that I mean using a multi-material or bimetallic solution in order to have enhanced material properties, whether it be hardness or corrosion resistance or some type of desired thermal properties. And then last but not least, really the heart of today's conversation, for repair applications. So you can add material to existing components, get them back into service much more quickly and typically more cost effectively as well. So with that, I will turn it back over to Laura.
Thank you, Melanie. I think we wanted to launch a quick poll question. So this should pop up for you, but on the right-hand side of your screen. And that is, what is your level of experience with metal additive manufacturing? So please feel free to, as we continue, put an answer in for that poll, and we'll check back in with that. Looks like Carl has launched that. Thank you. So the TBGA additive manufacturing maturity model, we developed this kind of early on in our consulting world. We've been around for 4 years, so it was about 3 years ago. And it helps describe basically the product requirements, the criticality of the product, and also the skills and knowledge that would be required to apply AM at that level. Because what we found was, of course, trying to describe prototyping level 0 requirements are quite light. It's just basically, hey, can you make something that's maybe the right shape, or is kind of descriptive of the future application. When you move up to level 1, this is where we're starting to have production influence, tools and fixtures. At this point, there is a criticality to the performance because, of course, we're needing those tools to do certain things. Sometimes it's heat, sometimes it's not expand too much, sometimes it's just generally not break. When you get up to level 2, this is where what we call a substitution level. So this is where you can use AM as a part-for-part replacement for traditional manufacturing. We've got a couple of examples of both level 1, which would be the tooling, as well as level 2 in these next couple of slides. When we get up to level 3 and then level 4, we're getting into a range where we're doing things that you can only use AM. We couldn't use traditional manufacturing to achieve those. So at level 4, I like to call this ninja level AM because the skills and knowledge and equipment and materials and people to get to that point are extremely, extremely high. So obviously we advocate for stepping your way up through the levels because you learn a lot as you go. But at level 4, basically, we're enhancing performance. We might be structurally and thermally optimizing at the same time. There's engineered features, and essentially at this level, you can only produce this product using additive manufacturing. So as we reflect on these different levels, how is DED used to achieve these product requirements? Next slide, please. So we'll go back. If there's any project managers out there, the classic triple constraint of schedule, scope, and cost come into play here as well. When we talk about level 1 in the tooling example, I think everyone is happy to save cost. That's always going to be something that is a driver. But when you're looking at tooling in particular, schedule is a huge deal as well. So anyone that's operated within aerospace shops or within automotive as well, while those schedule and those requirements are different for those different industries, all of them certainly would like to shorten the schedule of getting to end tooling. The other thing that sometimes will be enabled with that is you might be able to speed up your product development life cycle, even prior to getting into production using tooling, AM tooling as an enabler for that. And the final is scope. Melanie's already commented on it in the enhanced category. It's possible to enhance the performance. And in fact, with some of these applications, it's possible that the repaired version could have better performance than the original one, at which point you might even consider, hey, maybe I should just enhance this in the first place using DED. So there's a lot of those that tend to kind of play in. I'm going to pause. I think we can probably, yep, poll has ended. So what is your technical experience with metal additive manufacturing? It looks like the majority of our audience are novice with a few intermediates and a few advanced. So I will definitely encourage you as we go through these next use cases, feel free to populate things within the Q&A at whatever level you are, and we can help and hit some of those. Next slide, please.
Yeah, and I think, Laura, since that poll is done, why don't we do another poll? Since we're talking about different drivers in AM and what drives you to adopt AM, let's put up a poll that looks at what are people most interested in adopting AM for? Is it schedule, scope, cost, or maybe other? And I guess if you select other, maybe it's all of the above too. So let's see what people think about that as we go.
All right, sounds good. Looks like that one has launched as well. So I wanted to throw this level 4 AM enabled application out there because this is one that I personally have gotten to watch over the years. So MX3D is a company in the Netherlands that just recently installed a stainless steel bridge. It's actually in the red light district, but it's the first genuinely designed DED fully functional stainless steel bridge. And I actually got to stand on one of the prototypes about 3 years ago when we visited there. So it's really exciting to see that. But I think this highlights the magnitude and the diversity of DED, because Melanie is going to show you some amazing components done with blown powder, highly engineered. This is highly engineered in a different way and definitely at a different scale. And so they just did this installation. You can Google it and look at the examples. Next slide, please.
Yeah, I love that bridge example because it really goes to show the scale which can be achieved with AM. It's not just little things. It can go really big too and high throughput. So another example of a level 4 is the rocket nozzle. You can see it on the screen, and I have it here with me too, just so you can see the scale. So this is a scaled down version of what the actual size would be. But what's interesting about it is not only do you have some of the complexity and geometry with the internal cooling channels in the wall, as well as the change in shape and the diameter, but it's also a multi-material solution. So this can be achieved a number of ways. You can do a multi-material solution by building a part out of a base material and then adding material to the outside of it to give it that final layer, extra strength or corrosion resistance or whatever you might need it to be. But you can also do functionally graded materials, which is transitioning from one material to another or even multi-materials, but doing so with a gradient strategy. So you might be changing by 10% composition each layer. And there's some software out there now that can tell you, ideally, if you want to achieve certain properties, what that strategy needs to look like. So that's a whole other topic that we could deep dive, but it's just another really cool example of the power of additive. Back to you, Laura.
As a metallurgist, I've spent some time looking at people trying to figure out how to navigate phase diagrams so they can make good transitions between alloys using that. So it creates an opportunity that then has new problems that get to be solved with the material optimization. This next example is a set of applications at what we call TBGA level 2. And this is a production or a like-for-like replacement using additive. So in the bottom left-hand corner is a number of titanium components produced by Norsk Titanium in partnership with Spirit and Boeing. So the one in the top left of the bottom left, that's a little confusing, is actually flying on the 787 Dreamliner, and several other components are also flying. And so these are static components, but they have been fully qualified and are certified in flying on planes. In the top right-hand corner is an example. This intermediate compressor case is produced by GKN Aerospace over in Sweden, their engines division. And a small borescope boss is deposited using laser wire. So it's bigger than the size of my thumb, but not like a whole lot, to give you a feel for size. So the rest of that case is fabricated, but they needed a borescope boss in a new location, and so they chose to build it up with laser wire. And Melanie, I think you were going to tell us about that last application.
Yeah, sure. I love the second application you talked about, Laura, because it shows that the ability to also what I would call enhance. So if you have an existing component or an existing tool, you might not necessarily need to repair it, but let's say you have some type of design change and you need to be able to add a feature to it and change it. I mean, that's another great, tool that you can use this technology for. And so this component, I'll hold it up for scale. This is an Inconel 625 component that we made. And this is a replacement part for a NAVC component. It's a bracket that goes onto a ship that I believe it holds a light in place. And it's just a fixture that can break, and there's could be some supply chain challenges with it. And so this is a great sort of on-demand, application for, something breaks and we need to replace it. It hasn't been, optimized for, light weighting or anything like that. We just built it exactly the way that it's currently built today with additive. And then with this particular part, it can go into service as is, and there's not any post-processing specifically for this component.
Yeah, at this level, it's kind of interesting because often, particularly for spares type operations where you're looking to maybe get an aircraft back off the ground, or or a ship, or I guess it would be in the sea. These types of things when you're talking from a schedule standpoint, and these are the types of things where, from a cost standpoint, the cost might be through the roof for that individual component compared to a normal production one. But if you're able to produce a like component that can, have the performance required, there's a huge business case for inserting that. So we've shown several examples, one in a like-for-like production environment, which is probably a bit of a pathfinder to then try to go after even more critical and larger components. But this example of using things for spares and significantly reducing lead time, or point of use manufacturing as well, where perhaps it's hard to get replacement components wherever you happen to be, maybe due to supply chain disruptions or like a military application.
I guess Laura, since you brought up sort of the different drivers, like schedule and cost. The poll results are interesting, and 41% have said scope is the reason that they would adopt additive. So I thought that was really interesting. Only 12% said cost, and 12% said schedule, and 35 others. So I'm guessing a lot of the 35 might be, because it's some combination of those things, or maybe something completely different. But I think that's really interesting, and we're talking more about additive applications, at the moment. So it makes sense for, I think people have realized that you don't only adopt additive because you're trying to save on cost. But when you look on tooling, that equation can be different. So you can actually recognize cost savings for tooling, I think, sometimes even more advantageously than other types of applications. And then when we start talking about repair, again, I think that's another good example of not only can it help with your schedule or your scope, but also your cost, because many times you can repair something at a lower cost than you can remake it even traditionally. So do you have any other thoughts, Laura? I just thought the results were interesting.
But no, it is interesting. And I think, to your point, I think if we run, my guess based on this demographic, if we run this type of poll maybe 5 years ago, I think that maybe those answers might have been different. But I think that we're starting to see enough of those use cases where AM is being used to actually enhance performance. So maybe those level 3 and 4 applications. And I think that's something that powder bed fusion has done a good job of is opening up the eyes to the art of the possible. But then I think sometimes people will then look at directed energy and say, oh, I can't do that, which is of course incorrect because you can. And I mean, the bridge was an example, the rocket nozzle is an example. And there's quite a few different examples out there where you can do these level 3 and level 4 performance enhancements with DED. They just tend to be on large components, and sometimes they're more critical ones. So the qualification process for getting something flying on a plane or you know, in automotive are a little bit lengthier. All right, next slide, please. So this next application, we promised we would talk about tooling. So here we are, is an aerospace composites tool. And the face sheet for this was 3D printed in Invar. So that's a nickel-based steel. It's commonly used where in higher temperature applications. So Lincoln Electric Additive Solutions has this one out. They published it in Composites World. One of the problems that they had with this is they needed a tool material that closely matches the very low coefficient of thermal expansion for typical carbon fiber reinforced polymer. So the CFRP prepreg, when they went to cure this, they needed it not to be moving significantly. So you can't use something like aluminum, which is going to move all over the place. The old solution was during prototype and low volume production, tools were actually fabricated via hand layup and autoclave by the same material. So they used CFRP tools to then lay up the actual parts on. But part of the problem is those tools are not robust enough to use now in a production environment. So basically those had to be scrapped, and then you'd have to make a new round of tools. So this new solution was to use gas metal arc welding DED process to build the face sheet. You'll see that the backing for this tool, it still looks very traditional. And even within this article, they mentioned that the next level of opportunity would be you know, looking at the forces and the different requirements for the backing portion of that tool and using some generative design. DED processes certainly can do that, and you just put metal where you need that reinforcement. So there's definitely an opportunity to optimize that entire tool. But anyone that's kind of worked in the composites realm, and if you think about this, lead time on tooling like this would be very significant. And you'd also be struggling with, if you look at that depth, that aspect ratio for that tool, trying to figure out how to get that metal piece such that you could then go machine and finish off of that would be pretty significant with traditional manufacturing. So DED, of course, can move around, as Melanie mentioned, with the multi-axis. So I suspect that they put this face sheet, basically turned it in a vertical orientation, and we're able to print that. DED, similar to powder bed fusion, has its own kind of self-supporting angles, and then you have the possibility of adding some movement to the workpiece as well that gets you into additional geometries. So this is our first example of a level 1, which is indirect, but you can see the opportunities for both schedule as well as possibly cost implications for manufacturing tool using DED. Next slide, please.
Yeah, and this is a very simple tool that we were making with an automotive application, and this is a tool steel. It's H13. So you know, like Invar, which prints very nicely, we can also print tool steel. So you know, another benefit of DED, it does work with a fairly wide range of materials, and you know, sometimes tooling can be you know, somewhat unique type of materials that you don't hear about as much in additive, but it certainly can be done. You know, I wanted to show this example because there can be some challenges with working with H13 and tool steel in particular with respect to preheat. So there's definitely considerations to take into account with your tooling and the geometry and the material. In our case, we do automated preheat with an induction heater. So we can automate the process to put the tool in there, scan it to understand what needs to be repaired, and then have a induction heater that will come down within seconds, heat it up to the desired temperature, and then immediately begin deposition. And you're able to get a really nice bond and a really nice build that way. So just another simple tool example here that can be made out of H13.
Next slide, please. All right, so this is an example. I actually took the picture myself, but this was when I was down at Missouri S&T at their Center for Aerospace Manufacturing Technologies. I can't say the exact user of this tool, but I was allowed to take a picture of it. So it is an automotive tooling example used for sheet metal forming. And this particular automotive company has been using hybrid DED. So this is where they would do laser blown powder to deposit, and then CNC machine actually on the same machine. That's an option, or you can obviously do machining separate as well. And there's a number of things that we see as opportunities with this. As you can see, this type of tool, it has some pretty high aspect ratios. So that's kind of interesting for feature repair, but I know that there's steps beyond that where they have looked at whether they would do all of this for do DED for enhancing in the first place prior to needing a repair. So one of the opportunities there is to increase the abrasion resistance with hard surfacing alloys. So just because your substrate is one material, it doesn't mean that you can't coat that substrate with a different material that perhaps works well with it, but then provides some additional performance. Some other material examples, people are using cobalt-based alloys for superior hardness, as well as wear on H13 tool steels. And so, there's a few examples that people are talking about publicly. I suspect there's probably a few more that people are keeping close to their chest. But you can think about obviously the cost implications. If you've got an expensive tool and you've lost some feature fidelity on a portion of that tool, and it's failing with respect to your stamping dies, to repair and use that expensive die, obviously it's going to be a lot cheaper likely than going and producing an entire new one. Melanie and I both, it's kind of funny when you trade notes on where the cost bar is, and 25% cost reduction bogey seems pretty standard out there when we talk about what would be required to consider adoption of a technology is a minimum of a 25% cost. But these obviously would have schedule implications as well, get you back into production more quickly. And the other would be possible performance implications. As I mentioned, sometimes technologies that are being used for repair, once you go through and you do the testing for those, you actually realize that the repair performs better than what the original material did. And so often you'll see repairs that end up kind of moving from Melanie's repair category over to the enhanced category, where you say, well, I want that performance on my tool from the beginning. So perhaps you use DED to enhance the performance of the tool prior to it actually going into production. And there's a whole myriad of things and gaps that are there, but people are working to solve them, and barriers for this. But this is a whole category where some people are using the term remanufacture. So there's repair and remanufacture as another one. And some of that includes this process of being able to scan a workpiece and compare that to a native CAD model that basically says this is what it should be. Here's where it is. This is where it should be. And then having the software to go and plan those solutions. It fits in, and from a qualification standpoint, sometimes people are doing standard repairs and looking at all those things. So obviously that has to be matched up. Another area that people are really doing a lot of research, and again, Melanie's already started to talk about that, is in the materials side of things. Is how much do you need to preheat to make sure that you've got good bonding and interfaces and those types of things, but also, do your materials play well together? Do they have matching CTE or other things metallurgically where they do, intermetallic cracking and other problems like that? So there's a lot of research in this space that looks at optimizing materials for DED. But the good news is that for the most part, if it's blown powder, then it's, as long as the powder is, or the material is available in a powder form, you have the opportunity to try it. The other thing that I don't know that we've talked about quite as much is some people are also using DED for thermal performance. So if you have tools where you're maybe trying to reduce heat and pull some heat out or optimize your thermals, you can do copper, you can do other, higher conductivity alloys with DED. And I know that, Melly, maybe you want to comment on, because I know you've done quite a bit of copper DED as well.
Yeah, I mean, controlling your thermals is a great application for utilizing coppers, especially when you talk about, you might have areas that you want to be copper, and then for strength, you might need to add like a nickel super alloy to it. And that's a great application for, aerospace. If you think about controlling your heat for battery applications to extend battery life, there's a lot of really cool applications for being able to have very good control over your heat and where your thermals are. So that's absolutely true. I think since you mentioned like cooling channels, there's an example of I don't know if you can see in my camera, but there's a cavity here that goes along the wall, and this was to just kind of demonstrate that with DED you can do conformal cooling, although there's limitations to what the geometry can be for those channels. It is something else that's possible to be able to control your thermal properties in your tooling as well.
Excellent. I did see a comment in the chat regarding, oh, I'm in the wrong chat. All right, there we go. I said the image in the upper left appears to have a threaded hole. You stated there's no post-production work done. Does it make the threaded surface with additive? I think that was that part that you had made, Melanie.
Yeah, I mean, we typically, no, it wouldn't be a threaded surface. You would have to do some type of post-processing for that. In this case, it was just a through hole. But it depends on the size, of what you're trying to do. With DED, at least with powder DED, typically as the smallest we go would be about 0.6 millimeters. So it just depends how, fine of a feature you're doing and how, kind of small of a part. But typically, if we were going to have a threaded surface, that would be something that would be require post-processing.
Excellent. Great. I think that we've talked through our use cases, but I see that there's already a question popping up in the chat, and I really encourage anyone, if there's anything, whatever it is, technical, strategic, try to stump us, that's fine. Please put it in the Q&A.
Yeah, I have a question for you, Laura, while we wait for the audience to ask us some questions. Since there are quite a few people that seemed to be, a little bit newer or novice in additive manufacturing when we did our poll, if someone is new and they're like, okay, well, how do I get started? How do I know what to do? And, how do I start if I want to adopt it or want to look at it?
Yeah, absolutely. And as you can imagine, as a consultant in AM, we get asked this a lot. My first recommendation before you go and try to hurry and pick an AM process and select a process and get focused on applications is really evaluating your pain points. So those could be internal pain points, or those can be your customer pain points. So does it have to do with tooling lead time? Are you wanting to speed that up? Are there cost implications? Is it a safety thing? Safety and ergonomics within your shop. Once you understand those pain points and really understand where it is that you think you could have the most business value, then you go and you look at your AM processes and start to look and say, okay, is AM a solution for this? We really do not advocate for the AM hammer. Often people will buy will buy an expensive piece of equipment and then call us, and they're trying to figure it out, and they don't quite have the organizational knowledge yet, and they're kind of desperate to try to find a business case for it. The only caveat I'll have to that is if we're talking about desktop 3D printers and basic shop support, you should totally buy that and then go find uses for it because that is one that you will pay off again and again. If you give your engineers and your shop guys an additive tool to go and solve problems in the shop. I got to do that with a 1 million square foot machine shop when I was back at GKN when I hadn't gotten my 20 kilowatt laser DED machine yet. And it was awesome. The mindset that it created, we had guys within the tooling department that were printing things. I remember we printed a sound reducer. I don't know if anyone's listened to a Quackenbush drill before. It's where you're drilling through both, yeah, it's fun to say, both composites and metal. It is insanely loud. And so we prototyped a housing for it to help reduce the noise within the shop because there was extra hearing protection, all of these things required. So all of these things just because we had a desktop, 3D printer there. But yes, definitely focus on the pain points. But I'm going to flip that one on you, Melanie. And as a provider of DED product services, what is your role for someone that is either kind of first exploring or maybe they have some applications they'd like to kind of try out?
Yeah, I mean, that's a big part of the reason why we do services and R&D and feasibility studies in-house is to help that journey. So, we're happy to take a look at someone's application, or model or just discuss ideas. And if it's not a great fit for the DED process, we can typically identify that pretty quickly. And we aren't afraid to say that, in our mindset, additive manufacturing capabilities are just another tool in the toolbox. So, DED is not a, one size fits all. It's always the best application or the best tool for you. It really depends on your application and the materials and really what your end goals are. So that's something we typically talk to our customers. If they ask us if we can make something, we say, yes, what are you trying to achieve by having us do that versus the existing ways? And then, like you said, Laura, talk about the pain points. And, are you trying to, do a multi-material approach? Because if you are, then this is probably the only technology that can do it at this time. If you're just trying to make it cheaper, then we have to look at it. But I think it's important to, like you said, to really understand your pain points and then also understand that there's more tools in the toolbox. I obviously, love DD, think it's amazing. I know you do too, Laura, but it's not the only tool in the AM toolbox. So if you saw something today where you say, well, my application doesn't really fit into what they're talking about, don't give up on your AM journey yet. Out, Laura, or, feel free to reach out to me as well. And if it's a good fit for DED, I'm happy to talk to you about it. And then again, we can do feasibility studies in-house where we do some sample prints and just say, yes, it's something that's feasible. We can help with, the business case and the ROI of, why you would do the technology. And then we can do production as well. So if you say, yeah, this looks like a good fit for us, but we're not going to do the production in-house. We want you to do it. We can take that on as well. So we want to partner with our customers and help them on the additive journey. I like the TBGA maturity model because it graphically shows that additive manufacturing is a journey, and you have to start somewhere. So I guess that's the final piece that I would say is if you're interested in additive, jump in. Reach out to some service providers or reach out to someone like Laura and get started because you don't know what you don't know yet, right? And there's a lot of power in additive manufacturing.
I think it was a good segue to say that it's not always, DED is not the only tool out in the toolbox. Someone had asked, has anyone evaluated the new Xerox Metal 3D printer? I personally can say yes. From a technical standpoint, it's interesting. It uses a wire feedstock versus powder, and there's some nice safety implications as well as, depending on the material, some cost ones. But their liquid jetting process, I see some great opportunities for, like casting replacement. They're still at a relatively small size, and they're still kind of early in their technology journey. But I think it kind of has an interesting space that it could play in, that's not necessarily quite powder bed fusion, but somewhere in there. It still is quite a bit smaller from a scale standpoint than what we're usually looking at from a DED standpoint. So it's sitting definitely in a bit of a different application space. We want to take the surface roughness one, Melanie?
Yeah, sure. It's going to depend on, you know, quite a few factors, and of course that's one thing that we can work to optimize. If you have certain areas that either won't be able to be finished machined, or maybe just don't have quite as tight of tolerances, we can work to really reduce that roughness. And in addition to changing things like your spot size and your speeds and feeds, we can also do like a laser remelt and that kind of thing. But typically you could just say roughly like 25 to 50 micron is a good kind of range there.
Yeah, and that's specifically for a powder fed process, right?
Right.
Yeah, so the other thing, I'll see if I can hold this up. Here is an example of the laser wire deposition. This was made on that machine that I was standing behind. I consider that, you want to call it almost like an undulating surface, because you have, it's very smooth because each individual bead, it doesn't have the powder. It's fully liquefied and it just solidifies as you create that bead. However, you have this kind of smooth bumpiness that goes along. So that one, it's actually very hard to say because it's not a traditional surface roughness. The individual surface roughness is actually quite low. However, you have this undulating surface. So sometimes with these larger melt puddle DED processes, like some of these wire-fed ones, they just kind of have to take a look back at how you analyze that, because actually some of the fatigue performance and things like that have been analyzed on these, they actually can perform really well because you don't necessarily have any little stress concentration sites within it. So unfortunately, there's no easy answer. The answer is it depends. But just like what Melanie said, each of the DED processes kind of have a sweet spot, and you can always optimize for surface roughness. And more importantly, it's not even just about the surface roughness, but it's whatever that end performance requirement that you have that you're trying to meet.
Yeah, that's a good point. There's a question on here about how to obtain funding to acquire equipment. So we make our own equipment in-house. So we run FormAlloy systems, you know, in-house, so they're our own. But we have customers that have used a variety of techniques, I'll say, to obtain the equipment. Of course, capital equipment financing is one option. Another is if you can get, depending on if you're a small business or not, I'm not sure who's asking the question, but there are, you know, small business innovation research type of projects, and we do those fairly regularly. And we can typically partner with, you know, research institutes or other small businesses and, you know, make enhancements to our equipment or work on a particular application that might be of interest to one of those government sponsors. And that's another way to get funding to go do some of this work. So I hope they answered your question. Over asked that one.
Yeah, the other thing that I'll add to that is some states have grants and support as well with respect to advanced manufacturing equipment. So in addition to all the things that Melanie mentioned, the other thing that I'll note is whenever I was purchasing, you know, the equipment with GKN, the equipment didn't exist. So we were creating the specs with an integrator and doing all of that at the same time. This was about 7 or 8 years ago. Things have changed significantly since that time. And not only are there integrated machines like FormAlloy is what Melanie has, but there's also ones that are within a much more reasonable price point than there were previously. So not everyone has to go for the 20 kilowatt laser beams. I'm sure you hear that and think like, yes, there's giant price tags there. A lot of systems can operate with a much lower power laser, and so it really depends on the size of the parts and also what you're looking to do with the equipment.
Yeah, and to that point, Laura, we have quite a few machines in the field where people were just getting started or they're doing smaller things, and they start with a 500 watt laser, so it's one 500 watt laser. And then in the future, if they go bigger or want to do different materials, they might upgrade to a bigger laser. But you can do quite a bit with a, like you said, with the lower powered laser. It doesn't have to be the 20 kilowatt stuff. is a good lead-in, I think, to our next question was, for you, Laura, did you build the parts at 20 kilowatts?
We did not do much at 20 kilowatts. It was actually probably closer to 12 or so, somewhere kind of more in that range. One thing, whenever we were speccing that really large piece of equipment, we weren't speccing it for production. We were speccing it to be a research and development piece of equipment. So what we actually did is we bought 2 separate 10 kilowatt lasers and a combiner. Because what it allowed me to do is, at some point in the I didn't know where we were going to be operating, what our sweet spot was going to be for our power, but I just wanted to make sure I wasn't limited at just 10 kilowatts. But what that meant was, if at some point we wanted to separate those, and those lasers now go on 2 separate systems, there would be an opportunity to kind of separate that out. But I think it's really important to highlight, because those types of parts that Melanie is showing, you know, this is what we call small melt puddle, DED. And that piece of equipment and this part, you know, that I'm showing with the large beads, we call large melt puddle. And the way that you build up parts, the types of parts can be significantly different between those 2 types of systems.
Great. Okay, I'm going to take another question that I see here. Do you preheat other materials besides H13? Yes, we do. I'll say off the top of my head, the other material that's pretty common for us to preheat is copper. So if we are using a copper substrate, like if we have a copper component and we're doing a repair on it or a material addition to it, we do typically heat that, preheat that as well. And that's just because creating a melt pool on copper can be challenging, particularly with IR lasers that we most commonly use. And if you have a preheat, it just sort of accelerates that melt pool generation and, you know, makes your, you know, deposition adhere better and, you know, just be more efficient. So there's different materials and different reasons why you do a preheat. So that's something that we would look at. But I would say, you know, there's many materials that don't require preheat, so it definitely depends on the material.
Yeah, I'll add to that. I know we're talking about preheat. There's also the other end of the equation. So if you've done any traditional welding, say on titanium, you know, this concept of interpass temperatures and making sure that you're also not getting too hot. So for the large parts that we were doing at GKN, and it's nothing proprietary to this. Everybody knows that titanium gets hot and stays hot for quite a while. There was a lot going into build strategies and those types of things, basically to keep the titanium material within the sweet spot from a temperature standpoint, not too low and not too high. And that's true for quite a few different materials, because, you know, the heat evolution is going to affect your microstructure, which is then going to affect your future material performance.
Laura, I think this might be a good question for you. Have you compared laser DED to wire arc additive manufacturing productivity and print resolution?
Yeah, the more generic answer is yes. We certainly spent a lot of time before we even selected the laser wire process for developing that back at GKN. I have several former team members where if I say the term down select matrix, they kind of get a little shiver, have a little PTSD. We went through a long time of going and comparing those. There's interesting pros and cons with all of them, and it really comes down to what are the requirements that what are you trying to do with the technology? So people often ask me, hey, which one's better? And it's like, no, you have to be very specific. If you're working in steel and you want to do parts fast and you want to do them relatively cheaply, there's some wire arc, there's some plasma arc processes that are probably fit the bill and maybe doing exactly what you need it to be doing. For some of the other materials, sometimes titanium and Inconel, and depending on the types of applications that you're looking at, a laser-based process might be better. The other thing is what type of flexibility you want to have on your melt pool. One of the reasons that we chose the laser was because we could change the spot size. If I wanted to go down and do very fine melt puddle, like some of what Melanie is showing there, I could with my laser, because I could take the power down, I could change the spot size, I could do different optics. You don't necessarily have quite that level of flexibility to turn your melt pool up or down with some of the other arc-based processes. There's a certain limitation to that. So it really depends on your application and what performance and requirements you're looking to get out of it.
And there was another question, Laura, that came in about melt pool size differences. So it's kind of a good lead in to what you were just talking about. We typically work anywhere from about 0.5 millimeter all the way up to 6 millimeter. And so that's kind of the size range with powder DED. And like Laura said, there's different ways to achieve those different sizes that are fairly straightforward. It's not a complete machine reconfiguration if you want to go from a smaller spot size to a large spot size. But large to me is 6 or 8 millimeter in powder, and of course it can go much larger than that for some of the other applications that Laura talked about. So again, kind of just depends on what you want to achieve and finding the best technology for it.
Yeah, and to give you a feel for what would be medium or getting into large, closer to like a 12 millimeter kind of puddle, it's spot size and puddle. So this piece that I have right here, it's a single bead wall. So you can see that's pretty thick. It's a pretty large size. The WAM processes and wire arc processes, those types that you see, tend to be closer to that, I'll call at least a medium to larger melt puddle size.
Okay, there's another question here that I can take about the particle size of the metal powders for DED. So there's actually a DED cut for most powders, which is typically in the 45 to 105 micron size. Now, lower than that is typically what you would use for powder bed, and then of course you can go above that too. So again, I'm going to say it depends on your application. So although most commonly we use what's considered a DED cut, we can use powder bed, and that's actually powder bed cut powder, which is the smaller particle size distribution. And we would do that for things like if you wanted a very nice surface finish. That is one of the ways that we can achieve a better surface finish, is by actually using a smaller particle size powder. So I'll just say, that's another benefit of the powder DED process, is that you're fairly flexible on, the particle size, and, you can achieve different things with different types of powder. We've already, like I mentioned, we worked with a larger particle size as well, and it was a non-spherical powder that was actually a powder that would have been wasted. It was sort of a byproduct of the atomization process, and so depending on your application, if you don't mind is having some extra surface finish or surface roughness, it's another way to potentially decrease the cost of your materials going into the process, is to use a higher particle size, a larger particle size.
Yeah, I think it's cool that DED basically gets to use, so when you got your typical curve of powder size distribution, laser powder bed fusions down here, ED is kind of here, and then you have everything else. Well, guess what? DED fits into that everything else category. So if it's material that's being traditionally atomized for powder bed fusion, it's good from a pricing standpoint, because DED actually can go use the other portion of that cut and that distribution.
Yeah. And then to that, a question came in about safety issues with respect to powder bed grade powder. And that can certainly be an issue, particularly if it's a reactive type of material. If it's a reactive material, the larger the particle size, typically the better from a safety standpoint. But that's why, regardless if you're using powder bed powders, a DED cut, or some larger particle size, at least in our process, we always use a shield gas and within the build chamber. Whether if you're working in an inert environment, obviously you're in an inert environment, so you're not going to have the reactions with oxygen. But even if you're working in an ambient environment, we always use a shield gas, and argon is the gas that we use. But most powder process are going to have some type of shield gas for that safety reason.
Yeah, and I think it's important to note too, with it's true for DED, it's true for cold spray processes and things like that. the amount of material that you're not capturing, actually depositing, is relatively low. So it's not like you're having significant pile-ups of powder, as you might obviously managing a powder bed fusion process, as well as the depowdering part. So I think it's a little bit easier to control. And then the other thing, of course, is if you're not using those finer cuts, the safety implications aren't as severe. It's nice.
Going through here to see if there's any other questions that we didn't answer. There is some questions about the differences between powders and wire. And you know, what I can say is we would likely have to do some parameter development on a material if you're changing from powder or changing from wire to a powder or vice versa. There would definitely be some parameter development just because of, you know, how the powder flows is different than how the, you know, wire is deposited, and sort of the mechanics behind all that. So I wouldn't want to say yet, you know, you wouldn't be able to reuse anything from it, because I think if you're trying to do an additive process, it's always useful to have data from other processes just to help you kind of bound, you know, where you should be. But it would require some parameter development to be able to change between those processes.
Yeah, and I did see a couple questions around, you know, powders used in metal cord welding wire versus DED. I got to be honest, I don't know the specs off the top of my head for metal cord welding wire, but I mean, it's certainly one. I mean, you're welcome to reach out independently. I can take a look at that and see how similar or different those are.
Okay, well, I think we're pretty close to the end here. Maybe I'll just ask, you know, one more time if you have any question. Last chance, post it in the Q&A. If not, my email address is there. Laura's email address is there. You know, thank you again to SME for hosting us, and thank you so much, Laura, for agreeing to join me. It's always fun to get to talk about DED that we love and additive manufacturing. So
our favorite topic.
Thank you.
No, thank you, everyone. Thank you, Laura. Thank you, Melanie, for joining us today. Great discussion, super interesting. Obviously, additive is really shows that the power and the growth potential that it still continues to have. So, thank you for joining us. A lot of interesting questions that we covered today, and there's still more that are coming in. I like to think that we'll be able to pull a copy of the questions that are still coming in. And Melanie, if you don't mind, I'll send the hard copy of these questions, and we'll try to address everything if you don't mind. Special thanks to our guests, Melanie and Laura, for providing their insights in additive for metal. We appreciate your time and support of the manufacturing community and for supporting SME events. And of course, a very special thanks to all of our attendees who took time out of their day to spend with us. We appreciate it. And we hope that you certainly found this conversation to be informative and interesting. We will send out a quick survey, and we would appreciate any feedback that you could provide us. Your insight helps us process improve, I guess, and make better content when webinars down the road. So your time and spent on the survey would be appreciated. And finally, if we could just go on to the next month's promo slide. Be sure to join us August the 19th. Oh, that's a little bit wrong. It's not the 15th, but it's the 19th at 3 o'clock, where we're going to present the next M2 series webinar, Keys to Unlocking Industrial Insights to Detect and Prevent Performance Issues. Registration for that webinar is now open. So with that, again, thank you. Have a great rest of your day, and we'll see you next month for another edition of the M2 series webinar. Appreciate it. Have a good day.